So in a binary search tree, we have a algorithm which automatically finds the place for the element, whatever the new element is coming. So if this is the case, you can see the root element is 30, and every element that has come after 30 is greater than 30, and that's because because of that here there are so many elements are there at the right side. So we have all the right side of element, but there is nothing on the left side. Okay. So now because of this, what's happening is this entire tree which you are seeing over here is looking imbalanced, right? So right now this tree is unbalanced, right? Why? Because right subtree has around four nodes. So right subtree has four nodes, and the left subtree has zero nodes. Okay, so if we calculate the balance factor of balance at this 30, if we calculate the balance at this 30, so what will happen? Balance at 30 will be 0 left subtree minus 4. So this balance is minus 4. Okay, so the ideal balance that we can consider is minus 1, 0, or plus 1. So minus 1, so 0 will be the condition. So 0 can be condition when we have element like this. This is one element. It has one left element and it has one right element. So here right subtree also has only one, and here this also has only one element. Right. So in this case, if we check the balance at each subtree, so we can say over here is there is no element, there is no left and right element, so there is zero balance for this, there is zero balance for this, and here for this root node in the left subtree there is one, and there is right subtree there is one, so one minus one, that becomes zero. So this is completely balanced, right? Now, when it will be minus one and when it will be plus one, so let's say we have a tree like this. It has left subtree, and but at there is nothing over there in right, nothing is there. So in this case the length of left subtree is 1 and length of right subtree is 0. So in this case balancing is 1. Okay, and when we have next right subtree, right, so here only right is there, there is nothing on the left, right? So in this case, this will be 0 at left and 1 at the right. So here the balancing factor will be minus 1. Okay,
Yeah.
understood?
Yeah.
So when we have these situations like 0 or 1 or minus 1, we can say this is the accepted situation. We can say the tree is balanced. Okay, but when this condition disturbs, when this condition disturbs, we cannot say that now this is a balanced tree, right? So to make this balanced, we have to perform some rotations in this. Okay, so AVL tree is basically ABL tree. We can say this is automatically balanced tree. Okay, so in case of automatic balance, what it will do? Let's suppose we have to insert few elements like let's say um, I'll take the new one. Okay, so new. Okay, I will not save this. Now, let's say if one element is coming 30 over here. Okay, so 30 has come here. Now the next element comes at the right is it's coming 50. Okay, so when 30 comes, initially balance is 0. When 50 has come, so now balance at 50 is 0 and balance at 30 is -1. Okay, this is accepted. Now a new element comes. So when new element will come, what will happen? This um, um sorry. So when the new element will come, now let's say new element has come as 40. So 40 has come here. Now the length of, now this element has 0, this element has the balancing of 1, and this element has, since at right side there are three there are two values are there, and left, in left subtree there is nothing over there. So now this balance will be -2. So as soon this is -2, now balance is disturbed. So what it will do, so since it is in minus, right? So when it is in minus, it is clear that right subtree has more values. So when right subtree has more values, it will be rotated on left side. So here left rotation will be performed. As soon left rotation will be performed, 50 will come up, 30 will be at left. So here when left rotation will be performed, it will, this tree will be converted as 50 will come at up, 30 will be at this. Okay, and now since um, now 30 has come here. Now 40 cannot come at the right of this. So 40 will be considered as the right of 30, right? So 40 will come here. Okay. When we will be rotating like this, what will happen? Now, in this rotation, now you can see here when I have rotated like this. So now the balance has been changed, and here it is 2. Okay. In this case. But
Okay.
there can be
Sir,
cases
is
like,
this being recorded?
yes, yes, this is being
Okay, okay.
recorded. Okay, so here now you can see this is again disturb, and the balance is this was -2, now balance is 2. So when we'll be rotating like this, so again I need to perform the right rotation, but that will not be a possible case. So like this, it will be once it will be rotated to left, but then it will be rotated to right. So this will not be a feasible strategy. So we'll see how you will see slowly how we can do these things. Now let's say we have another case. Another case is like I'll explain all the scenarios one by one, and you will understand. Now let's say we have another scenario. This 40 is not there. Let's remove this 40 from here. Okay. And we have a case of like we have a new element inserted, and that new element is, let's say, it is 65. Okay. When this will be there, again, balance is 0. This is -1, and this will be -2. So now, in this case, when the rotation will be performed, then 50 will come up, 30 will be at the left of this. So this is a simple case. 30 will be at left of this, and 65 will be at right of this. Right. So
Okay.
now this will be 0, this will be also 0, and this will also be 0. So this is the simplest case, right?
Yeah.
Understood. So this is how the entire rotation needs to be performed. So we'll see various scenarios how these rotations needs to be performed, and how we can program these rotations in our code. Okay.
Okay.
So this is overall a structured scenario. In this structured scenario, we have to perform rotation immediately when the tree becomes unbalanced. Okay, immediately the rotation will be performed. We will not wait for entire tree to get constructed. Okay, one way is that let the entire tree be constructed, and then we'll balance. That will not be there. As soon the tree becomes unbalanced, immediately it will be converted to the balanced tree. Rotations will be performed, left or right rotation, whatever, wherever it is required, it will be performed and tree will be balanced immediately. Okay.
Okay.
The left and right means left is smaller and right is bigger. Trait will be follow here as well, and based on that only these rotations will be performed. So let's see how we can implement that. So where it is. Yeah. Okay. So I'll make a new program over here. EVL. Okay. We'll discuss all the cases whenever, wherever it will come. First, I'll
Yeah, yeah, yeah,
explain you the case, and
yeah.
then only we'll proceed for that implementation so that you can understand that. Okay. So now again for this we have to create the class. So this class will be same what we created in our binary search tree. So this is tree node we are creating. In tree node we'll define init, and will initiate it with the self comma data. Okay, the same structure, self dot data is equal to data, then self dot left is equal to none, and self dot right is equal to none. Okay. Now, since this is the structure of a tree. Now, apart from this, we also need to calculate height of this tree. Okay, so we'll include that in the height itself. So self dot height is equal to, and we'll keep this height as 1. Okay, and then as soon the data will come, we'll do that process further. Okay, so this height factor will now be involved with each node inside the tree. Okay,
Yeah.
so now we'll define def get height, and here we'll define the node. Okay, and here if not node if not node, then return 0, else return node dot height. So every step this height will be checked. Okay. So with this get height function, will get the height at every step. Okay. Now another very basic requirement now is to rotate left or to rotate right. So first of all, we'll create the function for left and right rotation, and then after that, we'll start the inserting process. Okay, because inserting will be same what we did in binary tree. In the same way it will be inserted, but after inserting we need the balance also. So as soon the balance will be checked, the rotation needs to be performed. So for that we'll create the rotation function first. Okay,
Okay.
so here we'll create the right rotation. And here we'll take, let's say y function, y value we are taking. Okay, and we'll print rotate the tree on right, and not tree, we basically rotate node. on right, and here we'll do y dot data. Okay, then when will be rotating right? How we have to do that process? So first of all, if we are rotating any node, so let's say we have a node. If we are rotating the node towards the y, then towards the right. So the left of that node needs to be preserved somewhere else. For example, um, where it is. For example, where is my tree I created? In this case, if we see if we are rotating on right side, so suppose we have this case here, we are going to rotate this 30. Let's say um, I'll create new one. Okay, let's say I have 30 over here, and I have taken um 20 at this place and 10 at this place. Okay, and when I'll be rotating this on right side, right? On rotating this on right side, what we have to do is we have to preserve the location of this element as well, right? Because when this will rotate right, the 20 will come up and 30 will go down. So we have to preserve the location of the left also. So that's what we are going to do here. Where it is, yeah. So that's what we are going to do. So we'll take x is equal to y dot left. Okay. As soon we'll perform this rotation, what will happen? Um, where as soon we'll perform this rotation, the lower node will come over here. Here what we'll do is we'll take a temporary node. Temporary node temp is equal to will be store x dot right. Okay. If x has right, it will come. Otherwise, it will be blank. And then y dot left is equal to um is equal to temp. Okay. If it has the right node. Okay. And then y y dot y dot height is equal to 1 plus. I'll just explain this how this is working. Max of get height get height of node y dot left and comma get height of y dot right. Okay, and in the same way, I'll take the x height. X height is equal to 1 plus max of get height get height x dot left comma get height x dot right. Okay, and then we'll return x. Okay, so now what basically we are doing in this right rotation, and in the same way we'll do the left rotation as well. What we are doing is, first of all, we are storing this x, this left of y at certain position, right? And then x of right, if right element has there, it will be stored to a temporary. and then y of left will be at temporary position. So this the entire right subtree of x means the left of that will be considered as the left of this. Okay, so how we can do this? And here we are checking again the height on y subtree and again the height on left subtree. Okay, so in the same way we'll do left rotation, and x will do over here. So if you are not able to understand this all in one, do not worry. When we'll implement, you will understand this, how these things are working. Okay, let the integration done its part. X dot data, then y is equal to x dot right. Yeah, there it was left over there, and then I am taking temp is equal to x to y dot left. Okay, and then y dot left is equal to no. Y dot left is equal to x. Y dot left is equal to x, and x dot right is equal to temp. And then we'll do the left again the height calculation. So x dot height is equal to 1 plus again max of the same thing. Get height of x of left, comma, get height of y dot right, not x dot right, and then y dot height is equal to 1 plus max of get height of y dot left, comma, get height of y dot right. Okay, so this is all going, and then at last we'll return y. So now I'll create the insert function, and then I'll then will do the entire processing. So in order, pre-order, and post-order will be same as it is what we discussed earlier. And now the main game is in insert function. We have already created the left rotation and right rotation. Now I'll create the insert function. Okay, insert, and here node and data. These two will be followed. Okay,
Okay.
I'll explain the entire process. Um, that how this entire code is working one by one. I'll take sufficient time to explain this. No worries, because it is a little advanced process of what we did in binary search tree. So insertion will be same as we did in the binary search tree. The additional process of rotation is involved over here.
Okay.
So once you understand this rotation process, you will be able to understand how these things are working. Okay, so I am just giving return tree node and data. If so, first of all, we'll write the same thing what we did in the binary search tree. Data is less than node dot data. Then node dot left is equal to again insert will be called insert node dot left, comma, data, and here, elif data is greater than node dot data, then it will be um, node dot write is equal to insert node node dot write comma data. Okay, this here. Okay, so by this insertion will be done. This we did in our normal tree also in our binary search tree. We did the same thing. So this is
Yeah.
the binary search tree. We did this just this part only, right?
Yeah.
Now, now our balancing will come. Okay, so let's say updating the balance on the nodes. How we can do? So to update the balance, node dot height is equal to 1 plus, and we'll do max of um get height get height node dot left comma get height node dot right. Okay, so by this we'll be updating the height at each one. Okay, so now what we are doing in this? Now you can see here I have made this this initially, right? So now what it is doing is basically if a node is existing, so get height function will be called. If node is not existing, it will return zero. Otherwise, it will again return the node dot height. So node dot height is getting calculated over here. So this is 1 plus and get height of left node and get height of right node, right? So here we are taking the maximum of whatever left is there and whatever right is there, and then we are updating this balance. Balance is equal to get balance of node. Okay, so get balance where we are doing get will create this get balance as well. um, So yeah, I have not created get balance. Okay, I'll create get balance and node. And here we'll do the subtraction operation. If not node, then return zero, else return get height, which yeah, get height of node dot left minus get height node dot right. Okay. So here in get balance, what we are doing is if node is passed, suppose over here in this node is passed. So what we'll do is we'll just take the left subtree and then we'll go to right and then height of right subtree will take and just will subtract from here. Okay, so as soon this process will continue, it will increase the height one by one, and then it will get the balance over here. Okay, so now by this we'll get the balance. Okay, now when this balance value gets disturbed, as soon this balance value gets disturbed for the node, what we'll do? We'll do the balancing, right? So balance the tree. So here we'll be balancing the tree. So for left subtree, left subtree. Okay, and here if balance is greater than 1. When balance is greater than 1 means if when balance is greater than 1, this refers that we have in at the left side we have more element than the right side. So when balance is more than 1, we need to perform the right rotation, right?
Yeah.
Balance is greater than 1 and and get balance of node dot left is greater than or equal to 0. Okay, so why we are doing this, I'll just explain in a while. And here we'll perform the right rotation, right rotation. Okay, and here we'll supply the node. In the same way, uh, again, yeah, here left. Well, there are different cases are there. Left, left. Then if it has left and right. So if balance is greater than 1 and get balance of node dot left is less than 0. Okay, then return. Then here we have to do node dot left is equal to left rotate rotate node dot left and then we'll return the right rotation. Right rotation. Okay. Now this left rotation part is completed. Now we'll do the right rotation. So let's understand this first now, then we'll do the right rotation. Um, let's understand this, what we are trying to do in this. And we'll let me make the in order function as well. Um, I'll make the in order function. I'll continue with this insert function on the right rotation further. Let me do this in order only. Left define in order and here we'll pass node. This will be same as what we did earlier. If node is none, if node is none, then return else in order node dot left, then print node dot data, comma, and is equal to and then in order, sorry, in order node dot right. Okay, I'm just making this function now. Let's save. Okay. Are you able to follow what we did so far in this?
Yes, sir. Yes, sir.
Okay, so now I'll share my paint screen.
1 second, sir. I got a call. 1 second.
Yes, sure, sure.
Okay.
Are you there? So here the case is this 30 is the node that is to be balanced, right? So it has the balancing factor as 2, and now it has a left child, and this left child also has one left child. Okay, so this is the case that we are discussing over here. Okay, so what is the condition? Balance is greater than 1. So this balance is at this node. Okay, then get balance. We are getting balance at node of left. Sorry, in this one. Balance is greater than 1. And so this balance is 2. And then we are getting the balance at the left subtree. Right? So at left subtree, balance, now here this balance is greater than 0, right? So greater than 0 means it is 1, greater than or equal to 0, both. So you can say if there is nothing over here, then also the same thing will work. Otherwise, if there is nothing over here, this will not work. So here only I'm talking about the left and left child. So here now only the one rotation will be performed, right? So this will be rotated at right. So that's what we have done. Return the right rotation of this node. So this is our 30 is the node. Here right rotation will be performed. It will be 30. Then it will be at left side. It will be 10 and sorry, not 30. When rotation will be performed, this value will be this value will be 15. This is 15 and 30 will be at right of this. So this is the case when we have the left and left. Okay,
Okay.
clear?
Yeah.
Now there is a second case. What is the second case? Let's say here I'll take the second case. Now here we have this 30 over here. Okay. Now it has a left child. So left child is, let's say, 15. And this left child also has a right child. Okay, so left child also has a right child. So let's say this is 20 over here. Okay, now at 20, this is 0. At 15, it is -1. And at 30, it is 2. Okay, so again, in this case, also 30 needs to be performed at the right side, need to be rotated at the right side. But the problem over here is if when I'll rotate this 30 over right side, so what will happen? 15, ideally 15 should come at top, 30 will be at right, but where 20 will go? Where 20 will go? So 20, because 20 cannot come at the left of the 15 because it is greater than 15. Understood?
Yeah.
Because this is greater than 15, so it cannot come at the left of 15, and at the right of 15 already 30 is there, right? So now what will happen here? We have to perform two rotations. What two rotations we have to perform? One is the left rotation. So left rotation of this. So this left subtree of this 30 will be rotated to left. So here, now this case will be, for in first step, this will be 30 and 20 will come at up and 15 will come at the left of this. Okay, this is the one step. And now at 30, the right rotation will be performed. So this will convert to this 30 and then, sorry, not 30. This will become 20. Okay, so here let me take this. So this will become 20. 30 will be at right of this and 15 will be at the left of this. Make sense?
Yeah.
Okay, so like this rotation will be performed. Now the balance at every element will be 0. Understood?
Yeah.
Okay, so that's what we are doing at this. So when balance is greater than 1, so here balance is greater than 1. You can see this is balance is 2, and Get balance, node of left is less than 0. So less than 0 means it has a right subtree. Okay, it has a right subtree. So when it has a right subtree, so at this point, first of all, this will be rotated. Okay, understood?
Yeah.
Okay, now there can be a question for you that what if we have both child of this left subtree? We'll discuss that in a short while. First of all, let us complete the rotation for the right as well, where it is. So as of now, we have done the rotation for left subtree only. Now we'll do the rotation of right subtree. Okay.
Yeah.
So where it is. Okay. Now for right subtree, we will write the code in the similar pattern that we did for the left subtree. Only the nodes will be changed to right. Okay. So here we'll do. So now balancing the tree at the from the right side towards left. So here now again we'll have the right case, right sub tree. Okay, so if balance is greater than 1 and get balance of node of right is greater than or equal to 0. Okay, so get balance is okay. Sorry, this will be minus 1. Here at right, when right subtree is more, our balance will be minus 1. Okay, and then this will be less than 0. Yeah, this will be less than 0. Then what we have to do? We have to just rotate to the left, return, left rotation, and no. What yeah, left rotation, right rotation functions, yes. Okay, then if now there will be next case of right and left balance, right and left sub tree. Okay, so if balance is greater than minus 1 and to get balance of node dot right is greater than 0. Okay, so now node dot right is equal to uh, right rotate rotate node dot right and then return left rotation rotation and help me with us node left rotation and right. Let me right rotation, left rotation. So right rotation. So where right rotation, left rotation, right rotation. Okay. And here left rotation. So left rotation, left rotation, left rotation. Okay, the same thing that we did. So now that for the left subtree, that in the same way will follow the this is the double rotation for the right subtree. So when there is a case of right and left, then first of all left subtree will be rotated for to the right, and then the main node will be rotated to left. Okay,
Okay.
understood? Any doubt?
No.
Okay. So Now we'll do this example. We'll execute this with the in by inserting some values, and then we'll see how these things are working. Okay, so let's see. So here I'll just execute this entire part. So entire function is executed now. I'll take initially root is equal to none. Then I'll insert um let's say insert list. I'll just create a list and just insert it one by one. Okay, so let's say I am inserting 30, 15, 20, then 67, 34, 21, 43, 44, and let's say I'm inserting 25. Okay, these things I'm inserting, and now I'll call a loop for numbers in insert underscore list, and root is equal to insert root dot numbers. That's it. And we'll make in order over here, and root I'll pass. Okay,
Yeah.
so I'll execute this now. There's no object at left. I have what I have created. Yeah, already I have created. So why where it has given the error? This is left insert left rotation. Okay. Um, why it is generating error? Object type has no attribute left. Have I not created any object over here? Um, tree node. 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 Okay. 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 This is right. Ideally, this should work. What can be the error? Why it is generating the error? Root insert root comma numbers. Are you able to find something?
I'm checking.
Hmm. Why it is written? Return tree node is right. Let me copy this tree node from here and return tree node. Yes. Okay. Now node is less than node data. Node dot left insert function. Okay. Everything is all right. Why it is giving error at this insert root dot numbers. Why it is giving that? Hmm.